Hello. If you don't know me, my name is Gavin Halliday. I'm one of the HPCC platform developers, and last year I took over from Richard Chapman to head up the team. In this breakout session, we'll take a look at different aspects of Roxie performance. We're going to start with the question of how do you investigate Roxie performance. We'll then explore the general problem of retrieving data from disk, and finally finish with a closer look at some of the more recent Roxie index changes. It's going to be a bit of a mixture of questions, new features, hints, and technical details. I hope all of it is accessible to everyone, and you manage to stay with me to the end. So first off, how do you speed up Roxie queries? Are they already as fast as they can be? Or do they have scope for large improvements? The problem with asking this question is that no two Roxie queries are the same. Some are simple and sequential, others are highly parallel. They may spend most of their time retrieving data, or calling other services, or performing calculations, or joining data together. How do you find out where the time is going in your query? In the past, the best bet has been to look at the summary lines that Roxie can generate in its log files. That sounds simple enough, but it's often a pain just to gather the logs before you look at the information. It can be even harder with the cloud environments. So now, when you submit a query, Roxie can return that summary information along with the query results. The example on the slide shows the extra option if you're using TestSocket. There's also easy access to this functionality from Easier Watch. I was hoping to include a screenshot, but it wasn't quite ready when this talk was recorded. If you go to the test pages for a query in the new release, the option should be obvious. So now you can easily get to these statistics. But what use are they? In the last year, we've used this summary information to help investigate the performance of various Roxie queries. We also added extra information when we found it wasn't enough to answer some of our questions, like, is there a bottleneck with index performance? If so, is the problem with the disk speed or elsewhere? How's the Linux page cache affecting performance? Is the problem with the Roxie agents? Is it a network problem, overloaded agents, or something else entirely? Or could it be that the client submitting the query is actually the bottleneck? Were we waiting a long time for it to read the results? For a simple query, the summary line may provide all the detail you need. Let's take a look at a few examples. Here, you can see SOAP calls are taking more than 2/3 of the time, so that's almost certainly the main bottleneck. Although, if you look closely, that still leaves 100 milliseconds unaccounted for. This is an example before the newer stats were added. Maybe they would help explain that missing time. And here is an example where a couple of function calls are taking a notable time. They're not the main cause of the slow response, but they're a reasonable proportion and definitely worth investigating. On this slide, the total time to load the index node is longer than the entire query. Is that a mistake? How can that be? It is because Roxie is executing multiple index operations in parallel, quite possibly for different index parts. Index read time is almost certainly the bottleneck. If these times were typical for this query, as the load increases, elapsed time may grow noticeably, as there'll be less spare capacity for performing work in parallel. Let's take a look at a couple of other values from that same query. The ratio of cache hits to adds gives you an idea of how well the index cache is working. Here, 10% of the branch requests and 75% of the leaf requests are going out to disk. That ratio will hopefully go down as the Roxie cluster warms up. But if it stays high, you should explore giving each node some more memory. We'll come back to that in a bit later. One final observation going back to that first example. There are some other curious numbers. The stats say that the agent took 380 milliseconds to process the index reads, but the Roxie server only waited for a total of 100 milliseconds for the results. That also doesn't seem to add up. It's another case of work being done in parallel, but this time within a single key join activity, rather than between multiple activities. If you're optimizing the configuration of a system, these summary lines are likely to be all the detail you need. If you're optimizing individual queries, we'll need to dig deeper to understand exactly what's going on. How do you do that? As well as the summary line, Roxie can also generate detailed timing information when you run a query. When you provide this option, Roxie creates a work unit that contains all the activity stats and returns the ID of the work unit along with the results. You can then view the special stats work unit in the normal way in ECL Watch. It's already available in ECL Watch on the test pages for the query in the bottom left corner, but the user interface will have changed by the time you see this video. Once you have your detailed activity timings, how do you know which ones matter? So, here are some example activity timings. Which of these activities is the bottleneck? Well, surely it must be activity A because it takes the longest time. That seems reasonable, but how about if I now show you the graph? In this graph, activity A executes in parallel with activities B and C. Yes, activity A is the slowest, but activities B and C execute sequentially, taking a total of 200 milliseconds. So they are actually the bottleneck because they're on the critical path. It's very often complicated. If, on the other hand, the concat was ordered or CPU resources are overstretched, then it might be a different story. The bottlenecks for a system under load can also be very different from when you're running a single query. When I tried to investigate the bottlenecks for a complicated query last year, I foolishly thought it would be easy. I soon discovered Roxie didn't record enough information to be able to work out the bottlenecks, especially when the critical path was within a chain of dependencies. A few iterations of the platform later, that's now been remedied. There's even a hotspot analyzer in ECL Watch, which takes the information from one of those stats work units and highlights which slow activities are on the critical path. Another consequence of those investigations was that Richard rewrote the algorithm that selects which activities should be executed in parallel. It now tries even harder to make sure that multiple SOAP calls, for example, overlap, even if they are in dependencies. So, recent versions of the platform have extended the stats available to developers and made them more accessible. Often, after some investigation, you'll discover a large proportion of your query time will be down to reading data from an index. This problem could be summed up in the question, how do you efficiently retrieve filtered data from a very large data set? It's a particularly important question when the data sets are orders of magnitude larger than the memory available in your server. It's a very common computing problem, and there are many different open source and commercial databases and key value stores that tackle it, each with different advantages and disadvantages. It's also one of the problems Roxie aims to solve. But before we look at the details of some of the Roxie changes, let's perform a bit of a thought experiment. We're going to ignore several important details, but I think the exercise is still instructive, and the results may not be quite what you expect. We'll make a few general assumptions. Let's assume our data is stored on disk, with multiple records grouped together somehow in blocks or nodes. We'll ignore the problem of finding the right node and concentrate on what happens once we know roughly where the data we're searching for is. Let's assume these nodes are compressed on disk, and after they've been read from disk, they may need some processing or decompression before they can be searched. And finally, let's assume that we can cache some of the recently read and decompressed nodes in memory. So, given those assumptions, how long does it take to return a match from a node? The search process goes something like this diagram. If the node's already in memory, then we can jump directly to the in-memory search and find the match. If it is not, then the node needs to be read from the disk, then decompressed or other processing, added to the cache, and then searched. What are some typical timings? These numbers are approximate, but they're reasonable estimates. Searching in memory is quick, a few microseconds, and that decompression time roughly matches our current implementation. Spinning disks probably take about 5 milliseconds for each read, while NVMe SSDs are much faster at, say, 150 microseconds. With those figures, what are the expected times to return a match from a node? Well, if everything's already in memory, then the search will take 5 microseconds. How about if 90% of the data is in memory? In that case, 10% of the requests will need to read from the disk and be decompressed. So the average time for an SSD will increase to 40 microseconds and hard disks to over 500. How about if only half the data is in memory or none of it? The table shows the expected average search times. As a higher proportion of the nodes are read from disk, the time quickly climbs. That's hardly front page news. Slightly surprising is that even if you keep half the data in memory, a slow disk kills your performance. With remote storage on the cloud typically taking a few milliseconds, the performance is closer to a hard disk than an SSD. And something else to notice is the effect of outliers. You may be very happy with your average query response time, but if one query has to read all its data from disk, the response time could double. If 90% of your data is in memory, you may even see an increase by a factor of 10. This was the problem we found using HPCC cache on Azure. When the data was in the cache, everything was great, but when it wasn't, the performance collapsed. So, how do you make sure index reads are quick? Surely, to get the best performance, all we need to do is make sure that in-memory cache is as large as possible. Unfortunately, as always, life isn't quite that simple. In reality, this is a more accurate diagram. When an application asks to read data from a file, the operating system doesn't necessarily read it from the disk. For instance, Linux has a page cache, which contains a copy of the data most recently read from the disk. It takes advantage of any unused memory, and when that memory is needed elsewhere, it evicts items from the cache. Note, this means that the memory used for the Linux page cache competes with any memory reserved for a cache of decompressed nodes. If you increase the size of the in-memory cache, there'll be less available for the disk cache. How quick is it to read from the page cache? Probably 10 microseconds or less. Let's calculate the same timings in our table. The reads from the page cache are faster than reading from SSD. Now there's one important difference between the disk and memory caches. The disk page cache contains copies of the disk nodes, which are compressed, while the Roxie memory cache contains decompressed nodes. This means we can fit more compressed nodes in the page cache than uncompressed nodes in the internal cache. So the question is it better to allocate memory to the memory cache or the disk cache? Well, let's assume our file has a fairly typical compression ratio of 1 to 5. For simplicity, we'll assume that we have enough memory to store all the compressed data in the disk cache, and that any disk or memory cache has been fully populated with data before we start. How are the timings affected by where the memory is used? Well, If all the memory is used for the page cache, then we've already calculated it will take 215 microseconds. If all the memory is allocated to the memory cache, it'll be able to store 20% of the data, because it takes up more memory when it's decompressed, so 80% of the nodes will need to be read from the disk. If we calculate the average search time, you get the numbers in the table. It's not what I would expect. This suggests using a memory cache of decompressed nodes is slower than relying on the page cache. Why? Because the costs of having to reload from disk for 80% of searches outweigh the savings avoiding decompression for 20%. The actual difference is almost certainly worse than this. You could get bonus marks if you can spot some reasons why. So, allocating all the memory to the memory cache is no good. How about if we split the memory, say 40% memory cache, 60% disk cache? Well, with 40% of the memory used by the internal memory cache, it can store 8% of the total nodes. 60% will be in the page cache, leaving 32% that need to be read from the disk. Again, more bonus points are available if you spot other simplifications. What timings do we get now? Timings are better than when all memory is allocated to the memory cache, but they're still slower than with just the disk cache. In fact, with our assumptions so far, using a memory cache is always slower on average. Does this mean an internal cache is a waste of time? When might it make a difference? Well, let's experiment with a few of our assumptions. How about if the node only expanded by a factor of 2 in memory? That will allow more pages to be held in the memory cache. Continuing with the memory cache using 40% of the memory, it can now hold 20% of the nodes, and only 20% would need to be read from disk. Finally, we have a case where the internal cache is worthwhile, when our data is not very compressible. Slightly counterintuitively, it's still only worth it for the SSDs, not the slower spinning disks, which I would have expected to benefit the most. Also, let's be careful about not drawing the wrong conclusion. This does not mean that avoiding compression will improve your performance. Poor compression means the index is bigger on disk, so a smaller proportion will fit in the disk cache. What it does mean is that reducing your expansion makes a memory cache more effective. In fact, if you completely avoid decompressing your data, then an internal cache always wins, because it can store the same amount of data, but each search avoids the cache read and decompression. Let's explore another aspect. One of the simplifications you may have spotted earlier was that we assumed data was accessed uniformly. In reality, some parts of the data are accessed much more frequently. What happens if half of the searches access 20% of the data and all the memory is used for the internal cache? So that means half the searches are in memory and half will have to read from disk. That's good. We have another situation where the internal cache improves performance, but again, only for the SSDs. In real life, this is why it's worth setting aside some memory for the Roxie memory cache, regardless of the compression, because some parts of the data will be accessed very frequently. Finally, as a last thought experiment, what effect would reducing the decompression time to 10 microseconds have? The timings in the last 3 rows of the table. Search times for a hard disk have barely budged. When reading from an SSD, the time has roughly halved. But the average search time for page in the page cache has gone down by nearly a factor of 10. Even though this search operation is only part of the work done by index reads, a speed up like this should make a noticeable difference. But also notice that the effectiveness of the internal cache for SSDs has changed. It's now more similar to the previous effectiveness for hard disks. The average search time, when all memory is allocated to the page cache, is now less than a fifth of the time when it's all used for the internal cache. Previously, it was 3/4. So, drawing it all together, what can we conclude from our thought experiment? We've seen how the optimum memory cache size depends on many factors, including the access patterns within the index, the compression ratio, how quick the underlying disk is, and the time taken to decompress a node. We've ignored other complications. For example, reading data from the disk cache will normally evict pages from the Linux page cache, but they don't fundamentally change the picture. Also, nothing in the previous discussion was tied to a particular implementation. The same factors affect any database or key value store. The size of the Roxie memory cache is controlled with these two settings. What should they be set to? In the real world, it's even more complicated. A single Roxie query may use multiple indexes, each with different sizes, compression ratios, and access patterns. Then you have multiple queries deployed onto the same Roxie cluster. It soon becomes impossible to model in detail. There's no simple answer to how big a memory cache should be. We can try and come up with some guidelines, but tuning will require some careful thought and measurement. Counterintuitively, we have seen smaller internal caches are likely to be best for slow disks. What should be clear is the benefit that Linux page cache provides. Given the complexity, is there any hope in selecting a good internal cache size? I've got two suggestions that might help. The first is to make use of the details that are now published for each index that it's built. Here's a screenshot from a recent version of the platform. The index summary page now provides information about how much space the index will occupy in memory, as well as on disk. This is useful because if you can ensure all of your branch nodes fit in memory cache, then it's likely to reduce your search times. My other suggestion is to run some experiments. Gather all the Roxie summary lines from the time that the system first starts up and track how the ratio of cache hits to misses changes over time. Plotting them on a graph should allow you to get a good idea of the proportion of the data that's accessed frequently. From that, it should be possible to estimate an effective cache size. Then finally run some tests with those sizes to verify the effect on performance. I think it would make a very interesting research project. We'll get to the new index format eventually, but before we do, I'm going to take a step back a bit and outline how the Roxie indexes work. They haven't fundamentally changed in the last 20 years. So, a Roxie index is implemented as a B tree using nodes that are fixed size on the disk. We typically use AK. There's a single branch node at the top root of the tree, which is searched for first. That provides a mapping between the keyed data and details of which node to search next. The search process is then repeated on the second level of the branch nodes until you get to a leaf node that contains the actual data. The number of branch nodes you need to traverse before you get to the leaf node varies with the size of the data. If you have a small index, then the root node may be sufficient. Larger datasets generally require 2 or 3 levels of branch nodes. Note, the number of branch levels also tends to depend on the size of the keyed data. Those nodes are fixed size, so the larger each key entry is, the fewer entries can fit into each branch node. Fewer entries in each branch node means that more layers are needed in the tree. This is one reason why it's important to define your indexes carefully. Data that's never used in the keyed filter should always be in the payload of an index. If a payload field is included in the keyed portion, it will be included in all the branch nodes. That wasted space will reduce the number of entries each node can hold and increase the number of branch nodes. I've seen examples where moving incorrectly key fields to the payload was enough to remove a level from the search tree. That's an easy way to potentially improve your search performance. Anyway, back to the discussion. Note how frequently branch nodes are accessed compared with leaf nodes. Each search starts from the root node, and you're likely to search 2 or 3 branch nodes before you reach a leaf. This is one reason why search performance is critically dependent on the proportion of the branch nodes in memory. They make up maybe 1% of the data, but each one is accessed 100 times as often as the individual leaf nodes. When they're held in memory, the leaf and branch nodes are normally represented as a sorted list of rows. In the branch nodes, the rows contain the key fields and the position of the next node to search. In the leaf nodes, they're the complete rows. Searching a node in memory is simply a binary search of those lists. So, that's an outline of the state of play before version 9. How could we improve this implementation? Here's a list of some possibilities. Most of them are self-evident. They either reduce the time taken to do some of the work, like searching or decompression, or they increase the effectiveness of the internal or page caches. Our original idea was to focus on D and see if we could improve the number of nodes that can be held in memory. As we saw earlier, reducing the expansion factor to 2 made the internal cache significantly more effective, and the current index implementation expands the rows when they are read from disk. Could we come up with an index format that didn't need to be decompressed when it was read into memory? Rather than storing a list of rows, how could the same information be stored compressed, but in a way that could be searched directly? We experimented with several different ideas. The final solution is similar to a compressed, serialized representation of a prefix tree. It's simplest to illustrate it with an example. So, let's say we have the following 8 names stored in a 7-character string field. In the old format, that's exactly what the node contents would look like, a list of 7-character strings. The new key representation looks something like this. The first character can either be an A or a B. If it's an A, then it must be followed by B, but then there are 3 options for the next letter. If it's an E, then the next character must be an L, and the rest of the field should be space padded. Let's take a look at another example. How about searching for the name Ben? The first character matches B. As we walk the structure, we note we have skipped 3 items that started with A. Then we try to match the second character, E. We skip 2 items that start with A. E sorts before I, so we now know that we do not have a match. From our accumulated tally of skipped items, we know the search string Ben would come after the 5th item in the list. In each case, we walk the structure and the search finishes either when the next character fails to match any of the options, or we have matched the full key. The actual serialized structure also contains some offsets, so those options can be efficiently skipped. It looks like this structure may have the side effect of compressing the data, because any shared leading components are only stored once, but it won't help with any trailing fields. So we also added some other optimizations to help reduce the size for some other common cases. Indexes often use fixed size strings, so it makes sense to compress repeated spaces, and phone numbers or addresses often contain sequence of numbers or characters, so we compress those. So we implemented this for branch nodes, built some indexes with the new format. What did we find? Slightly to our surprise, the approach seemed to work. The new compressed format could be searched in about the same time as the old format. The nodes now don't need to be decompressed, so they're available more quickly. However, before we get too excited, the existing branch nodes use a simpler compression that takes about 20 microseconds to expand, so the time difference isn't really significant. Just avoiding the decompression would be a win. However, it proved better than that. The new compressed branch format also seems to compress better than the old format. For the examples we've looked at so far, the branch nodes take up about half the space on disk and a third to a fifth of the space when they're in memory, compared with the old format. There's significant variations between indexes, but the results so far are very promising. Better compression means fewer branch nodes in each level, which means the level above needs fewer entries. On one example, it removed a level of branch nodes from the search tree path in at least one example. So our next thought was, could something similar be applied to the leaf nodes? We decided the best approach was to split the leaf data in two, compress the keyed portion using the same compression as the branch nodes, and use a different compression for the payload. The existing leaf nodes use LZW compression. It compresses effectively, but it's not particularly quick to decompress. To allow us to explore different ideas, we made the payload compression for this new format configurable. Then we experimented. We looked at column compression, compressing single rows and blocks of rows, using custom dictionaries, and row compression that didn't need to be expanded in memory. In the end, we settled on using LZ4 compression as the default, because it was general purpose, compresses well, and is very fast at decompressing. What were the results? Here they are. The search times have very similar characteristics to the branch nodes. I haven't looked in detail, but I suspect they may be slightly faster, because entries in the leaf node tend to share the same leading key components. The key portion doesn't need to be decompressed, so we save there. More significantly, the payload decompression is much faster. Earlier, we explored the effect a change like this would have on the speed to search a leaf node. They were significant, especially when they came from a disk cache. Although the whole purpose of searching the nodes is only one aspect of an index read or key join activity, I'd expect this to have a noticeable effect on performance. Because the key portion is not decompressed, it takes up less memory. There are some similar savings for the optional file position fields. On average, the disk size is fairly similar. In most cases, it's a bit smaller. We haven't had enough time to further explore which indexes don't compress as well. And the number of leaf nodes is proportional to the size on disk. So for the cases where the disk size is smaller, it may contribute to removing a layer from the tree. So all in all, the results so far show a lot of potential. There's also some scope for future improvements. Because the payload is compressed separately, we could delay expansion until it was actually needed. If your searches return no matches commonly, or only count the number of matches, then you could avoid decompressing completely. We could also only keep a few recent pages expanded and re-expand them on demand. That would allow many more entries to be kept in the memory cache. With the much faster decompression, it may even give us the best of both worlds. We have several other ideas to improve the compression of the key portion. For example, using dictionaries of common words. We'll return to those ideas once we've had more experience with real-world indexes. And finally, part of the problem with the Linux page cache is that old pages are evicted when you read new data from the disk. If we use direct I/O, we could avoid those issues, but it's not clear that it will always be better. because we'd lose the benefit of the page cache being shared between processes. How do you use it? Actually, your first question really should be, is it safe? It's no good if it's really fast but loses your data. As part of the testing, we've rebuilt a wide range of existing indexes with the new format and checked that the contents are identical. We've also taken a look at the changes in sizes and compression and started to get a few ideas on the performance impact. I think it's got great potential, but until we try it in anger for some production queries, we won't really know how significant any performance improvements are. So we really need to put it into use and start to measure the difference it makes. Hopefully by now you'll be really keen to try. What do you need to do? Well, there are lots of reasons to upgrade to the latest version of the platform. This is just one of them. Do not use versions of 9.0 before .20 though, otherwise you'll generate indexes that are incompatible with the final format. You need to add a compressed attribute to your index definitions or build statements. The new format isn't created automatically because the new indexes are not compatible with older versions of the platform. A good first step is probably to build old and new versions of the indexes at the same time. On the slide, you can see a few examples of the new compressed syntax. You can add the option to either the index or the build statements. The second build example illustrates using a different compression for the payload. LZ4HC compresses more effectively, but takes longer to build. It may be worth it for some indexes. The final example also sets an option to increase the compression level. I really wouldn't recommend it for general use because it significantly increases the build time. Note, you don't need to make any other changes to your code. As long as your platform supports it, any query code will use either format, or even a mixture of the two. While you're adding the new attributes, take the opportunity to review your indexes. Are there fields that are keyed that should be in the payload? This will help performance whatever format you use, but it can make even more of a difference with the new format because the keyed and payload fields are compressed differently. And finally, let us know how it goes, either good or bad. Did it make a difference? If yes, how much? If no, why not? Any questions? Please feel free to ask us. Yeah, so I hope you are interested in the new format and that this talk has given you some insight into how to optimize your Roxie queries. If you do have any questions, then please feel free to email me or Krishna, who's been starting to work with some of the business units to test the new format. Thank you.